Just 10 to 2. It's California time.
Yeah, we usually don't.
5 minutes.
5, you know.
Yeah. Kind of let people think about it and go to the talk.
That's right.
How are you doing?
Give a chance to tell us some jokes.
Yeah, go be, tell us jokes.
Either you or the candidate.
Or like a preview of coming attractions, you know, like.
Yeah. Okay, so I'll just give you a preview of coming attraction. So this is basically a pillow, and he's going to show us how to render this pillow, how to draw this pillow. So the basic idea behind Shuang's work, Shuang is of course graduated from Cornell, a PhD, and then he's a postdoc at MIT right now. And he is famous for his work of data-based modeling. Basically, like how do you show the appearance of objects, not just using surfaces of the object, but volume of the object, how the light interacts with the object in volumes, not surfaces. And he was the first to do a CT scan of an object and then use the actual data to simulate the appearance of the object. So he has very accomplished publication record, even in his PhD, and just less than 1 year in MIT. He has got over 11 SIGGRAPH publications. So it is phenomenal productivity and contribution to the field. And he's a trendsetter in terms of how to do data-based modeling of appearance of materials. Okay, without further ado,
Thank
you.
you for the very nice introduction, and thank you for coming. So today I'm going to talk about some of my prior research on bringing virtual computer-generated images to the next level. Sorry.
Is there a microphone?
For the
My
recording?
microphone's on the floor, but for the house, there's no one.
Okay, you can hear them.
Yeah, I have a microphone on the ground.
Okay, sounds good.
Okay, so yeah, let's get started. So I work in the field of computer graphics, which is about building virtual realities. So in particular, my research aims to build virtual worlds that appear exactly the same as the physical one. Such as the Matrix. Although we are still far from being able to build the Matrix, physical accuracy has become the key to many important applications. In architectural design, for example, computer-generated images help to give an impression on how a modern building would look like before it is built. These images need to be accurate enough so that they closely match the reality. Otherwise, they would have little use or even be misleading. In retail, there's currently a trend of advertising using computer-generated images. IKEA, for example, started using these images in their catalog several years ago. Here, physical accuracy is important for giving customers a precise understanding about the items. In virtual prototyping, computer models are used to simulate the appearance of final products. This technique helps to quickly explore many design options, such as changing the color of this car. Virtual prototyping saves a lot of time and money that would otherwise be required to build physical prototypes. So where we are now, what quality can be achieved when using computer to generate images that reproduce real-world appearances? Traditional methods have had some success in handling materials with relatively simple optical properties, such as smooth metal surfaces or smooth plastics. For more complex materials that are important to many other applications, unfortunately, computationally reproducing their appearance remains a challenge. Let's look at an example. Here we show a computer-rendered sweater. It doesn't quite look like a real one. To understand what limited the quality of this image, let's look at how it is generated. Generating this image requires solving an integral equation called the rendering equation. This equation, in fact, has been the central one for 3D rendering or even the entire computer graphics for decades. Let me briefly explain how it works. Under this formulation, the surface is modeled as a set of smooth surfaces. Or some lag going on. So to get the amount of light leaving from some surface location x with direction omega, we consider all other points on the surface pointing towards x. This incoming light is then weighted by a material term that controls the local reflectance, and a geometry term that tells how much light is able to transmit between any pair of surface points. In the rendering equation, you can see that material and geometry are completely separated. In addition, light interacts with material in a local manner. It only interacts with the material at one point, x, where the light hits the surface. This abstraction, although used almost exclusively in computer graphics, has many limitations. In the real world, many objects, such as a fuzzy toy, cannot be simply described using a small number of smooth surfaces. Others, like a cloud, do not even have a well-defined surface to start with. In addition, in reality, light often interacts with material in non-local ways. In particular, many real-world materials allow light to scatter inside, leading to a translucent appearance. This effect is often called subsurface scattering, cannot be easily handled using traditional surface-based methods. So to overcome these limitations, one way is to go beyond 2D surfaces and treat objects as 3D volumes. Here, the 3D volumes are used to describe the optical properties of an object, and is fundamentally different from those used in 3D visualization. So my research takes this route. In particular, I take real measurements represented as 3D volumes. In addition, I develop new algorithms to think beyond surfaces so that we can fully and efficiently utilize the measured real-world data. So before diving into the details, let me give a brief description on volumetric light transport. In fact, this technique has been used in many other fields for a long time. Because of some practical limitations, it's relatively new to graphics, and I will discuss these limitations later. So in this volumetric formulation, a scene is allowed to contain 3D volumes in which light can scatter around. So this model is able to capture very complicated light-material interactions. Each time when light scatters, its new direction and intensity is determined by a set of scattering parameters. In particular, the optical density controls how often light scatters. The denser a material, the more often light scatters. Then the single scattering albedo controls how much light is lost at each scattering. The higher this coefficient, the less amount of light will be lost, so the object will overall become brighter. Finally, the phase function controls the distribution of light's new direction given its original. So in the volumetric framework, geometry and material are no longer separated. This is because the spatial variation of scattering parameters, especially the density value, is able to capture very fine 3D structures. Light-material interaction is not local anymore either. This is because when light enters a volumetric medium, it can affect a region around the entrance point. So in theory, it can even affect the whole volume. So now we know roughly how the volumetric light transport works. Let me tell you more about my research. At a higher level, my research looked at the problem of where to put the interface between geometry and material. I will explain exactly what this means in the next slide. And at a lower level, my research tackled some practical challenges that had limited the use of the volumetric approach in computer graphics. So let's start with the high-level story. So we have seen that under the volumetric framework, geometry and material are connected components. So because of this, to reproduce some real-world appearance, we can control which part we handle using geometry and which part using material. So for instance, to achieve a certain level of accuracy or a certain level of quality, it is possible to use a crude representation of geometry, such as a low-resolution volume. In this case, we can leave all the complexity on the material side, which normally means we need a phase function that has a high dimensionality because we need it to have its most general form. Another possibility is to use a finer representation on geometry. This may allow us to simplify the material representation, possibly by lowering its dimensionality. Of course, we can go to the other extreme by leaving most complexity in geometry. In this case, it is possible to use relatively simple material models to achieve a similar level of resulting accuracy. So the question is, which approach should we take? In fact, there's no single answer to this question because it depends on our goal and the amount of resource that we can afford. But this is an important question because the answer to it largely determines the limits of the corresponding techniques. Unfortunately, this question is often overlooked. People tend to stick with a particular geometric or material representation when modeling real-world appearance. So my research looked at the full range of possibilities. In today's talk, I will focus on the last approach, which is the most untraditional and leads to very powerful tools for modeling fabric appearance. I will discuss other possibilities as well. I have introduced my research from a higher level. So next, let me tell you more about the practical limitations that significantly limited the use of the volumetric approach and how my work try to tackle them. Although the volumetric framework has been around for quite a while, there are several limitations that stopped people from using it in computer graphics. The first obstacle lies in data acquisition. You can imagine that to acquire or to recover the scattering parameters from a physical sample requires measurements underneath its surface. So comparing to traditional reflectance measurement frameworks, this is a much harder problem. So the difficulties in acquiring real data force people to build models manually from scratch. So previously, the volumetric models are often built procedurally. which means specialized programs need to be written to create these models. And writing such programs can take a lot of manual effort and even be frustrating. To create this virtual scarf, for example, even requires implementing a SIGGRAPH paper that can take months. And another problem for these procedurally generated models is their lack of irregularities. These irregularities arises naturally. So as a result, you can see here, they look unreal at a close distance. The third obstacle is in simulating light transport for volumes. When light enters a volume, it can scatter many, many times before being able to leave. This means we have to simulate a very large number of scatterings for each light path, making the simulation process extremely expensive. So let me tell you a real story here. I worked on a research project collaborated with researchers from Harvard, where we needed to render this image. Because the main focus of this project is physical accuracy, we decided to use the most brute force rendering algorithm so that we have the fewest possible approximations. As a result, it takes 10 hours. This single image takes 10 hours to render on a cluster of 2,000 CPU cores. And we had to burn $4,000 on Amazon EC2 to do this. That's a crazy amount of money, right? So we have seen the obstacles that stop the use of volumetric approaches. Next, I will present some of my recent work that takes one step forward, overcoming these challenges while keeping the geometry versus material question in mind. In particular, we introduced fundamentally new ways to create detailed volumetric models for fabrics based on real-world measurements. In addition, we developed new algorithms to simulate light transport within these detailed models, an order of magnitude faster than standard methods. So in this work, we focused on fabric, a kind of material that's essential to our daily lives. They're used to create clothing as well as many functional clothes, from window curtains to bed sheets. In computer graphics, fabrics have been studied for decades. However, modeling and reproducing their appearance remains a challenge. This is mainly due to the great variance of fabric appearance. Some of them, such as this silk satin, appear light, smooth, and shiny. Others, like the velvet and the fleece, looks thick, heavy, and fuzzy. Previously, many specialized models are designed to capture this appearance, but still, they have a difficulty to accurately matching the reality, especially for the thicker ones. So we developed a new technique to model fabric appearance. Our technique not only has the generality to handle a wide variety of fabrics, but also brings the quality of computer-generated fabrics to the whole next level. In fact, this is the first model that offers fiber-level details. As you can see here, each individual fiber is visible. This work has been presented at SIGGRAPH 2011 and recently republished at Communications of the ACN as research highlights. So our approach takes measurements of real-world fabric samples and automatically create volumetric models with rich details. Let me explain how it works. We start with the question on why do fabrics appear the way they do? In fact, the answer largely lies in their structure. So let's look at an example. Well, let's first look at how the fabrics are formed. A fabric contains a number of yarns. So this is part of a yarn. And each yarn, in turn, contains many little fibers. So this is a single one. So how these yarns and fibers are arranged largely determines the appearance of a fabric. So here we show two examples. The satin weave often look light and shiny, and the plain one look rough and diffuse. If looking closely, we can see that the top surface of the satin weave contain mostly aligned yarns. It is this coherence that lead to light reflected into narrow range of directions, causing this highlight, all these specular highlights and this smoothness. On the plain weave, on the other hand, we have interlacing yarns on its surface, and this causes light to get reflected into all directions, resulting in a rougher appearance. So to summarize, fabric appearance is driven by its small scale properties, such as the geometry and color of the fibers. How this property determines the final appearance is governed by standard light transport rules. So traditional methods do not put enough complexity in geometry, so they cannot resolve all these small scale properties. So to capture the widely varying appearance caused by the variation of such small scale structures, they have to use complex material models. And the complex material models are often expensive or even impractical because of their high dimensionalities. So our approach, on the other hand, puts enough complexity in geometry so that we can explicitly reason about what's going on at a small scale. So as a result, we can use a relatively simple material model to handle all these greatly varying appearance. Comparing to traditional methods that rely on high-dimensional material data, our method uses detailed 3D geometry that is much more trackable. That is why our method outperforms traditional ones on both generality and quality. This is not something that you can normally get because you normally need to trade one for the other. So our contributions include the idea of modeling fabric appearance based on their fiber level properties. To realize this idea, we developed new algorithms to recover such properties and turn them into full appearance models. Next, let me give more details on these algorithms. A fabric's small-scale properties include the underlying yarns and fibers' geometric structure, as well as their optical properties, such as colors. So we designed an end-to-end pipeline to recover such information from physical samples. Let's start with retrieving the geometric structures. In terms of a fabric's geometric structure, we are interested in two kinds of information. First, we want to know in a cloth volume where the fibers are. Second, we want to know at each fiber location which direction does the fiber go locally. This property is important for correctly simulate specular highlights. But then the question is how to acquire this information from real samples. The fibers are so small, and some of them are hidden beneath the sample surface. So we, for the first time, introduced the use of volume imaging technology in material appearance modeling. In particular, we use X-ray microtomography, or micro-CT, to measure the geometric structure of fabric samples. For each sample, we spent a couple $100 US to have it scanned. Thanks for the development of micro-CT technology, this scanning cost has been dropping. And the output of this process is a stack of 2D grayscale 2D images that are 2D slices of the measured volume. So here we show the scan result for velvet and silk satin, where the brighter regions correspond to cloth fibers. The CT scans, however, do not give us all information we need. So we need to process these images to extract such information. So the goal of this CT image processing step is to figure out the fiber location and directions everywhere in the scan volume. We use a technique introduced in textile research to do this. In particular, we start with computing the direction of fibers. We do this by applying an oriented filter to the raw CT data. This step works similarly as using Gabor filters to detect edges in 2D images, although in this case we have 3D data. And in this result, the computed directions are encoded in false colors, where the green pixels indicating fibers that go vertically, and red ones correspond to horizontally going fibers. So after that, to obtain the fiber location, we basically look at the filter response from the previous step. If the response is greater than a certain threshold, then we consider a certain point as being fiber. This is a 3D visualization of the resulting density field for silk satin. Hopefully you can see the vertically going fibers on its ground surface. We have got the structural information of a physical sample. Now let's look at how to obtain the optical ones. Because we already have very detailed geometric structure, we now can use relatively simple material models for the fibers. So in particular, we want to know their colors. In addition, we want to know how shiny they are. In this work, we make a very important assumption that the fabric is homogeneous, which means all the fibers are the same. This makes these two parameters global attributes. Later in this talk, I will discuss how to relax this assumption. So to find proper values of these parameters, we designed a process called appearance matching. We take a photo of the same material sample and try to find such parameter values so that a rendered image under the same lighting and viewing configurations matches the photo. In particular, we try to match two statistical measures, the mean and standard deviation of pixel intensities. These measures are computed within manually selected regions indicated with white rectangles. We do this because we want to avoid involving background or out of focus regions. In fact, these two measures are closely related to the two parameters that we are looking for. In particular, you can imagine if we make the fibers to have a brighter color, then the rendered image will also become brighter, which means a higher mean pixel value, and vice versa. And fiber glossiness and standard deviation have a similar relationship. Given this monotonicity, we designed a two-stage binary search algorithm to numerically find proper values for these two parameters. Now let me show some results for this appearance matching stage. The left image is a photograph. That's the target for this matching process. And the right image is a rendered one using the solved parameters. And the second pair of images are used not for appearance matching, but for validation. In the photo, you can see that when we rotate the sample by 90 degrees and draping it on the same base geometry, the highlights disappear. This is because the alignment of fibers on the surface of this material has created a highly anisotropic reflectance. Our model is aware of such structure, so it successfully predicts the vanishing highlights. Here we show another result for gabardine wool. Based on the scanned geometry, our method is able to reproduce the detailed texture on its surface. For validation, we switched to a novel lighting under which the texture is more pronounced. Again, because we know the underlying geometry, we successfully captures this effect. So these results further demonstrated that with detailed geometry, one relatively simple material model is able to capture very complex visual effects. So finally, we got a complete volumetric model that can be rendered. So this is a summary of our approach. First, we retrieve the geometric structure of a fabric sample through a CT image processing step. Then we use an appearance matching step guided by a single photograph to recover the optical properties. Okay, should we try to turn off the light, or is this good enough? Oh, maybe we should try. So now we show rendered results using the models built with our method. Here's a render of silk satin, which has a structure of mainly parallel yarns on its surface. Our model is able to capture these effects and convey a convincing impression of silk satin. And this is a rendered video of the same material. Notice the smoothly moving highlights on its surface. Oh, it's not moving. Move a little bit. There's some lag going on.
Is this a video?
No, this is the video. Okay. For gabardine wool, the variation in texture with respect to illumination direction is an important appearance characteristic. Our model successfully captures the subtle variation in texture across its surface. So next we show velvet. Velvet has a visible surface composed with fibers that stick up from the base material. This results in a very distinctive grazing angle highlight. This effect has been difficult to model. For our method, on the other hand, all these highlights emerges automatically from the scan structure. And felt is a non-woven textile consisting of a disorganized layer of matted fibers. Our model captures the fuzziness and thickness of this material, which in turn has been difficult to capture using traditional methods. So, okay, we are done with the results. In summary, we have demonstrated that coupling detailed geometry and relatively simple material is able to lead to fabric appearance models with better generality and next level quality. In practice, we introduced the use of micro-CT to acquire the geometric structure from real samples. And to use this CT data, we developed new algorithms to turn them into full appearance models. Next, I will briefly go over my other work that extends this work to support fabrics with different kinds of yarns or even complex designs. In this work, we proposed a new algorithm to synthesize cloth models from a scanned database. This work has been published in SIGGRAPH 2012, and our paper image has showed up on the front cover of the conference proceedings. In reality, an industrial loom takes physical materials plus a weave pattern specifying the design and physically create fabrics. We, in this work, created a virtual loom that takes the same design specification, but coupled with a scanned database to create virtual fabrics. We collaborated with textile designers at Rhode Island School of Design to validate our approach. Here we show the photos of a number of fabrics with a number of different designs that the designers created for us. Our approach, when taking the same design input, is able to create virtual fabrics that matches the reality fairly well. As a result, we have been working together to build a system to preview their fabric designs. So our approach starts with scanning a few fabrics with elementary patterns. We then chop this scanned volumes into little blocks, and then create a database. Using this database, we can synthesize a very large volume using a structure-aware synthesis algorithm. In this volume, every block is a copy of one from the exemplar database. Our algorithm carefully selects candidate blocks so that we can ensure a good resulting quality. Okay, now I'll show some renderings of the synthesized models. Should we turn off the light again? Thanks. Here is the fabric with a wavy twill pattern. The synthesis step itself only takes a few seconds. Our approach does a good job maintaining a smooth shading across its surface. Here we show a damask cloth where the golden and red regions have different weave patterns. We can see these patterns from close-up views. This pillow has a fancy jacquard weave pattern. Our method successfully captures its richly detailed surface structure. Okay. Our structure-aware synthesis algorithm has pushed model construction one step forward by supporting models with complex and user-specified designs. The detailed models generated by our approach offers a quality that has never been achieved. However, the complexity of these models also poses a big challenge for light transport simulation. Next, I will briefly present my other work to tackle this problem. We introduced a pre-computation-based algorithm to quickly simulate light transport within highly detailed volumes. This work was published in SIGGRAPH 2013. Earlier in this talk, we focused on building highly detailed models. These models often contain billions or even trillions of voxels. And such complexity makes the light transport simulation very slow, normally taking tens to hundreds of core hours for a single image. So the goal of this work is to render such volumes up to an order of magnitude faster. Our approach focused on cloth, but can also generalize to other materials. Recall that our models are created by replicating a small number of examples. Our idea for accelerating the rendering process is to pre-compute certain light transports for each exemplar, and then modularly combine such information on the fly. Our technical contribution includes a new way to formulate light transport in highly detailed volumes. And we provide a Monte Carlo matrix inversion-based algorithm to make our approach scalable to very large volumes, those with billions of blocks. Our pipeline Let me first go over a small number of definitions. Recall that in the final volume, we have equal-sized blocks, each of which comes from an exemplar database. So this is an example with just 3 blocks. We further subdivide each block into a small number of voxels. And we define each surface shared by 2 neighboring blocks as interfaces. And we further define patches as oriented voxel faces on an interface. So based on these definitions, we define 3 types of light transfer: voxel to voxel, patch to patch, or patch to voxel. Because there's only a small number of examples, we can pre-compute these transfers for each of them. Notice that once a single pre-computation is done, it can be reused on all volumes synthesized from this single one database. Now we know what to pre-compute. Next, let me give a brief description on our runtime evaluation process. This component contains 3 steps. First, we evaluate incoming light or source flux inside the volume. Then we use a modular flux transfer framework to propagate such energy into the entire volume. And finally, we do a final gathering step to generate the image. So you may ask, where do the speedups come from? Well, it's mainly caused by our modular flux transfer step, because based on the pre-computed information, we can propagate energy way more efficiently than doing brute force simulations. So that's why our method runs an order of magnitude faster than standard ones. Okay, next let me show some results, again, generated by our approach. You can have the lights off. Those are basically the last set of results. Here we show a shiny fabric with 250,000 blocks synthesized from just a set of 25 examples. It takes 90 minutes to render on a single server. When accelerated with our method, we get a very good match with a 9x speedup. This is a bright velvet with characteristic grading angle highlights. The thickness of this material causes the rendering time to be 192 minutes. Our method achieves a 13x speedup with a very good accuracy. Here we switch to another set of results synthesized from 120 examples. This pre-computation can be reused to speed up rendering of different designs. So this is one design. Our method achieves a 7.2x speedup and the result is visually indistinguishable from the ground truth. So here's another design under a different lighting condition. Based on the same pre-computation, our method again offers a 7.2x speedup. And when zooming in, we can see the detailed surface structures demonstrating the complexity of this volume. Our method also generalizes to non-cloth materials. This is a piece of finished wood represented with a volume. The complexity of this volume is nowhere close to those we just saw. In this case, our method still offers a 3x speedup. So to summarize, we developed a new technique to accelerate the rendering of the highly detailed volumetric models by exploiting the modularity. And such modularity is introduced by the previous model creation step. So up till now, we have focused on fabrics. Next, let me very briefly go over some of my other work that focus on more general cases or other materials. Earlier in this talk, we have focused on using complex geometry. If looking at the material side, existing models or phase functions are largely oversimplified. They cannot accurately reproduce the appearance of many real-world materials, such as this white jade or these soaps, even when they do not have very complicated surface structure. To tackle this problem, we developed new techniques that enriched our phase function arsenal. And this is the one that took $4,000. In volumetric light transport, the mapping between material property and final appearance is not one-to-one. In other words, there can be multiple scattering parameters that lead to the same material property. We introduced a new theory which studies this fact and provides fundamental insights into the structure of scattering parameter space. In practice, we developed new algorithms to find altered parameters that would lead to the same appearance but renders faster. So people can simply replace their material property using ones given by our approach to obtain effort-free speedup because they do not have to modify their underlying algorithm or anything. They just change their input. I have also worked on a number of other projects in physically based rendering and material appearance modeling. So despite the contribution made by my previous work, there remains a lot of problems to look at. I believe solving these problems will not only lead to fascinating computer graphics applications, but also can have an impact in many other fields. At a higher level, I believe precise understanding of the physical world helps us to build high-fidelity virtual realities. Given the rapid development of all kinds of acquisition technology, from 3D laser scanning to volume imaging, it has never been this easy to get this detailed information about the world around us. However, raw measurements themselves have little use. We need to develop new algorithms to turn these measurement data into basic building blocks of next-level virtual realism. At a lower level, we have seen that volumetric light transport allows us to control the interface between geometry and material. Ideally, we want to combine powerful geometry and powerful material to achieve ultimate quality. But in practice, we normally only have crude geometric representations and oversimplified material models. So there remains a lot to do for deriving powerful new material models and acquiring and representing detailed geometries. On the geometry side, for example, I'm interested to see if the idea we used to handle fabrics can be extended to handle many other materials with complex structures. Although in this case, we might need new ways to acquire their geometry. For example, snow will simply melt in a micro CT scanner. We need something else. We have discussed the possible ways to put the interface. It's interesting, in the future, it's interesting to consider if it's possible to connect these different approaches. One example is multi-scale rendering. Given a volumetric model, the problem is to create different versions with simpler geometry, but results in a similar appearance. So the difficulty here is to derive the new material models, which are trackable, which are not too high-dimensional, but can lead to good accuracy. Such techniques is useful to make the detailed volumetric models accessible to interactive or even mobile applications, where the amount of storage or the computation is limited. There are many other interesting problems in appearance modeling and physically based rendering that I think is worth investigating. I believe by solving all these challenging and exciting problems, we will one day be able to create virtual realities as realistic as the Matrix. I want to thank my advisors, collaborators, office mates, and friends for their help and support. And thank you for your attention.
Question, Jay?
Yeah, I have some questions about the work being done in film and computer games. They also need to have realistic looking images, and they have to make them in real time. Your methods don't seem quite to achieve real-time implementation yet.
Yeah.
Would you comment on their use of, for example, density estimation, reconstructions of the solution of the transport equation?
So first, I would say that movie is normally not real-time either. The current industrial standard for a movie is about 20 minutes to create a single frame, which means computing a full CG movie can easily take about half a year. So that's for movies. Games, they do need interactive performance. And that's why a lot of graphics doesn't look as good in games. Still in the game story, they normally do not do the volume approach because of the challenge in simulating light transport in volumes. It's still kind of difficult to achieve interactive or real-time performance. What I plan to look at next is kind of related to the multi-scale story I just mentioned. We now have very detailed models. Can we somehow make use of them in situations where we do not quite need such high quality? Can we simplify the geometry to some level so that we have less data so that we can simulate things faster? That is exactly something that I'm looking at right now. But yeah, so the interaction side is important.
With the current advancement in 3D printing,
Mhm.
Do you see possibilities of reversing the pipeline?
I mean,
Like, can you really print new fabrics and kind of, because you have models
Mhm.
now?
yeah, there is a work from Microsoft Research Asia that tried to 3D print fabric-like materials. So I think it's going to be possible. Although at this point, we don't have the material so that the fabrics are really behave like fabrics. We'll probably get some plastic that look like fabrics. But yeah, this is possible, and it's a very interesting
So I think your
area
work
to
will
look
be
at.
useful.
It is very useful to give them the structure that they need so they can print something. But there are challenges about what material to use and things like that.
Could you replace the CT scan with a very high resolution picture?
Picture?
Yeah. Photo and then infer some depth, some 3D structure. That would be.
Yeah, it's possible. There are following up work from other universities that tried to do the reverse engineering business from photographs. I wouldn't say their quality is as good as ours, but it's possible to have a pipeline that give you some information about the arrangement of fibers, yarns, so that you can use them to create like yarn level rendering. So yeah, there are following up work towards this direction.
Follow up on Pierre's question. You have pictures, photographs, and then when you say reverse engineer, you have photographs and you have a photograph of the surface and the material properties from the given lighting direction and all those things. From that, can you reverse engineer, deduce the underlying structure?
I would say if you only have normal scale photos, the reverse engineering would be a very under-constrained problem. So you need a lot of prior knowledge or something to recover the 3D geometry. If you have microscopic photograph, which we actually have tried, there are other problems. First, those microscopes do not give you highly calibrated measurements. Those things normally behave more like a webcam. You have some sort of image, but you don't know how, if they applied any weird image processing things to them. So it's kind of hard to tell the physical. You had to get physical quantities out of those images. And also under that scale, things kind of look crazy. Everything looks transparent. So I think it's possible to get some sort of information out of that, but it's going to be a not true.
Oh, you mean the micro level images, everything looks transparent. It's not, you cannot get a structure, it's right.
So if some of the depth capturing technology can make its way to the microscope, that would be more useful than current technology that you want to do it with pictures.
There is actually one technique that can be useful and is available now. There's a thing called gel sight. It's actually a paper presented right after us in the same section as SIGGRAPH, right after this paper. They designed a device with a gel on one end. If you push the gel onto some surface, it deforms, right? It has the shape. And it measures from the other side. So it can get a very detailed micron resolution normal map kind of thing. So that kind of technique will be very useful. Although it's kind of still incomplete because we only get the surface things. We don't really know what's going on beneath. So for very, say, thick materials, that's still problematic. And also you have to contact. The contact itself might change the shape of certain things. But at a higher level, this sort of technology can be very useful. Let me see if I can.
So you talked about, I have another question. So you talked about billions and billions, billion times billion matrices, and its inversion, right?
Yeah.
So to order to reconstruct all these material properties, you have to have that inverting that matrix. What was the technique that you did use to have?
Yeah, so for the techniques I presented, the reverse engineering part still assume homogeneity, which means the unknowns are kind of global. So we don't have to solve for spatially varying parameters. So in that case, the optimization is simpler. Otherwise, it's going to be super under constraint, like billions of unknowns. So what we did in this project is the simple binary search thing. We actually have a following up work that's currently under minor revision at TOC, where we did a more rigorous reverse engineering in terms of appearance. You can imagine we measured the same material under different lighting and viewing conditions and try to match all of them. And in that case, we used basically stochastic approximation, stochastic gradient descent, to optimize the optical properties. There are some technical challenges there because material properties, well, to get the image, you have to run through a Monte Carlo process. If you change the material property, it basically changes the probability distribution for that Monte Carlo process. So what do you do to take derivatives with respect to these distributional parameters? We use something called likelihood ratio method to estimate the derivatives in an unbiased manner. So later we did some more rigorous optimization, but still we assumed homogeneity so that we don't have a badly under-constrained problem. But you can imagine we can extend this, relax this assumption a little bit by saying we know that there are two kinds of yarns. So instead of having a billion unknowns, we probably have two copies of material parameters.
Any other question? Okay, thank you. Thanks.